Welcome to the Rambus Design Summit. I'm your host, Tim Messagy, and to kick off, we've got a keynote presentation from Rambus Fellow and Distinguished Inventor, Dr. Stephen Wu.
Hi everyone, my name is Stephen Wu, and today I'll be talking about emerging compute architectures for the evolving data center. Over the past 2 decades, our world has become increasingly connected, and processing continues to evolve from the familiar cloud computing paradigm into one where the edge provides a new opportunity to do some processing. One of the consequences of greater connectivity has been the explosion of digital data in the world, which by even the most conservative estimates continues to double nearly every 2 to 3 years. All processing architectures, whether they're in the data center, at the edge, or in the endpoints, have evolved to become more data-centric in order to continue improving performance and power efficiency. There are several key challenges that the industry faces, including the growing difficulties that are associated with data movement seen in all different computing paradigms. As these processing architectures have become more aware, we find that it becomes increasingly challenging to provide more memory and interconnect bandwidth. And we find that some of the tools that the industry has relied on over the past couple of decades, Moore's law and Dennard scaling, have either ended or are slowing dramatically. Just at the time that we need them as an industry in order to continue improving performance and power efficiency, these tools are really no longer available to us. We've seen many of these types of problems before in the high-performance computing world, where specialized architectures and accelerators have been used to continue to improve performance within a growing set of constraints. Data centers are beginning to adopt many of the things that we've seen in the high-performance computing world, and we're generally seeing a greater convergence between both the technology and the application approaches in both the high-performance computing world and within data centers, and we expect this to continue moving forward. There are several key drivers for how data centers will evolve in the future, and in particular, how memory systems will evolve. One of the big drivers that we're seeing is a move towards disaggregation and composability. Memory itself is a major portion of server cost, and at the scales that we're talking about in data centers, which can have tens of thousands to 100,000 servers within a single data center, underutilized resources can have a big negative impact to TCO. Another issue that we see is that the current replacement model today calls for entire servers to be replaced at the same time. In reality, if we take a look at the individual technologies which compose a server, we find that the CPUs, the memory, and the storage have different life cycles. And in order to improve and maximize TCO, we'd really like to be able to replace each of these key technologies on their more natural technology development life cycles. Another driver that I'll talk about a little bit later in this talk is AI processing. AI training in particular continues to be an extremely demanding workload, and we're seeing lots of new silicon and lots of new software techniques and models that are being used to address this problem and advance the field. AI processing in particular requires the fastest and most power efficient DRAMs. And we find that one of the challenges, especially in memory systems, is that the models and the training sets themselves continue to grow at a rate far faster than any other technology curve. At scale, especially for the larger neural network models, and when we're talking about training in the data center, we tend to use multiple engines to do the training. And one of the requirements then is that we have fast interconnects as well as fast memory systems in order to support communication and coordination between the multiple engines used to train these models. I first want to talk about some of the changes that are going to be coming to memory systems and that are going to move us towards a path where we can get to disaggregation of those resources and composability in the future. In the first panel here, we see that we're going to be having a new memory technology, DDR5. Near the end of this year, we'll begin to see servers announced, and in 2022, we'll actually see a ramp up of processors and servers that support this new memory technology. DDR5 improves upon the predecessor technology, DDR4, by giving more bandwidth, more capacity, and better power efficiency. DDR5 relies on the same kind of infrastructure we see today. Those DDR5 DIMM modules will attach directly to the CPUs using DIMM sockets. And so in that way, they'll look very similar to servers that we see today. But later on next year, what we'll begin to see is the introduction of a new type of link technology called the Compute Express Link, or CXL. One of the really nice features of CXL is it allows us to attach additional memory to processors outside of the direct DIMM slot attachment that we see today. So servers will not only be able to populate memory in those DIMM sockets, they'll also be able to attach additional memory through these new CXL links. The memory itself can be DRAM, it can be flash memory, and it can also be any of the new kinds of emerging storage class memories. And the memory can also be attached and put into the system using different form factors. We can have form factors that look much more like DIMMs do today, or we can even have things like add-in card form factors that allow us to have different kinds of capabilities for the memory that we add. By allowing us to add memory on these CXL links, it allows our platforms now to expand both the memory capacity and the memory bandwidth available to the processor. Now, once that capability is enabled, that will further enable the capability to have full disaggregation. So instead of just having the new memory attached a little bit further away than the local connections that are provided by the DIMM sockets, we'll now be able to move those individual resources like memory much further away, and we'll be able to completely disaggregate them from each other. On the right here, you can see an example of disaggregation where each of the resources, which is more tightly coupled today within the server, things like the CPUs, the memory, the storage, and the accelerators, they can each be moved into their own pools. And those pools can then be drawn from based on the needs of the workload. We may have a workload that requires a lot of CPU capability, a little bit of memory, and a little bit of storage. And what we do is we allocate those resources from these pools as needed. Once we're done, those resources can be put back into the pools. And the next workload may actually require a different arrangement and a different combination of those resources. And in this way, what we can do is we can improve the utilization of our resources, which allows us to get to better TCO and better end user experiences. Across these changes, memory systems are going to continue to evolve. They'll need to continue providing more bandwidth, more capacity, and more performance and power efficiency. They'll also need to improve the capabilities of security. As we begin to take some of these components out of the server and begin to pool them and share them across multiple users, then security is going to need to be improved not only for the infrastructure itself, but also for the data. One of the drivers towards the move to disaggregation is actually shown in this pie chart here. What can be a bit surprising is to realize that if you look at the breakdown of the costs of components in your typical servers within a data center, we find that DRAM composes about half the cost of a server. What's interesting here is that with memory being a major portion of server cost, it's important to have that memory be heavily utilized. But one of the challenges is that servers can be sized with their memory capacity to handle some of the worst case workloads. And in the average case, that means that memory is sometimes underutilized. When we're talking about data centers with tens of thousands to 100,000 servers in them, the aggregate amount of underutilized resources can be quite high. And especially for something like DRAM, if you've got a very expensive type of resource, you want to make sure that the underutilization is minimized. We also see that data center workloads themselves are evolving and they're becoming much more broad in their behavior. Data center applications, there are some that require very small footprints, but some that require very large footprints. and the ability to have some of these resources pooled where a server can actually be allocated the right amount of memory for that job makes it capable, that infrastructure, of supporting a broader range of workloads. And finally, because CPUs have a life cycle that's different than things like memory and storage, it makes a lot of sense to try and disaggregate these components. New CPU architectures come out about every 2 years, but for memory, especially for DRAM, new DRAM standards come out about every 5 or 6 years. And so if we wanted to replace an entire server just to upgrade the CPUs, it means that we're actually removing memory that still has some good usable life left in it. And so being able to, again, replace those components on separate timescales allows us to improve our TCO. I'm showing a little bit more detail about how CXL can improve the memory bandwidth and capacity that's available to servers in the next generation. On the left here, what you see is a typical workhorse dual socket server that's used across many data centers today. It's a single configuration that typically is replicated tens of thousands to 100,000 times within a data center. And in the future, because of the diversity of workloads, what we'll be able to do with expansion buses like CXL is to provide a range of configurations that can be reconfigured relatively easily. So in the middle panel here, what we see is that we can easily support 2 different kinds of servers with a CXL bus. And so at the top here, we might have one type of server that handles the memory capacity and bandwidth needs of a large fraction of the workloads in a data center. But there's always going to be some workloads that need more memory bandwidth and more memory capacity. What we can do is relatively easily add more memory through the CXL links in different form factors. They can be form factors that are closer to something that looks like a DIMM, or they can be similar to things like PCI Express add-in cards today. Either way, those coherent links will allow us to be able to freely add more memory as needed to meet both the bandwidth and capacity expansion needs of some platforms that are needed to meet the needs of some of the more demanding applications. A little bit more information here about disaggregation and composability. There's a lot of work going on in the industry right now, and one approach, which is shown here on the left, was recently discussed by Microsoft at one of their industry conferences. Their approach is to take the major components and to separate them into different racks. And what they're studying now is if you have maybe your CPUs are all aggregated together in one rack, you might have your memory aggregated together in another rack, other accelerators like GPUs, and then you might have I/O devices and local storage as well in yet another rack. The idea here is that you can have software defined composable infrastructure where when a job comes in, you aggregate together however many CPU resources you need, together with however much memory and maybe accelerator resources as well, and local storage and I/O too. Another approach is shown here on the right, and that's what's being discussed by the Compute Express Link Consortium. And this is an interesting diagram which actually shows how they propose to support pooling. On the left half of the diagram here, what you can see is at the top, these small squares represent different compute resources. And the rectangles at the bottom represent memory nodes, which have large pools of memory in them. The multiple compute engines are connected to the memory nodes through a CXL switch. And what that allows the system to do is individual compute nodes can allocate one or more memory nodes as they need for the particular jobs they're working on. But it actually gets better than that. So it's possible with CXL to try and share the memory at a much finer granularity. And so instead of having whole memory nodes allocated to individual compute resources, it's actually possible to partition some of the memory capacity and bandwidth within a memory node to individual servers, and that will allow us to get a better utilization of those resources. And again, it will lead to better TCO. Some of the interesting questions that come up, though, are really, when you have multiple ways of allocating memory, and when you have multiple ways of aggregating the resources together, the question is really what is the best way to do that aggregation and disaggregation of the components in order to achieve the best TCO benefits, especially at scale. There are other interesting challenges that are presented to software developers and programmers and compiler writers to really try and figure out what is the best way that these things should be presented to users. And so one of the big interesting questions that's being studied in the industry now is what are the best ways to make some of these things transparent to users? And what are the best ways to expose them to users so they can take full advantage of what's available to them? I'm going to move on now to talk about another one of the key drivers in the data center, and that's AI applications, and especially AI silicon. What we find here is that AI is very heavily memory bandwidth dependent. And so in this slide, we're seeing some of the various memory systems of choice that are used especially for AI training in the data center. On the left here, one of the popular options is to use on-chip memory, SRAM, and that is, it has a lot of advantages. One of them is that it's by far the highest bandwidth and most power efficient type of memory. The challenge is that it's really limited in terms of its overall capacity. Today, on a typical reticle size die, we can get a few hundred megabytes of capacity. And the issue is really if you can fit your whole model and your training data within that on-chip memory, it's a great solution. But the challenge really is that we've seen these models, and especially the training sets, are growing dramatically in size. They're growing by an order of magnitude or more per year. And so it makes it very, very difficult in a lot of cases to use on-chip memory for the training process. Still, there are others like Cerebras who have done some really incredible work to do full wafer scale processing engines. But even so, the amount of capacity that's available in these wafer scale engines is still much less than what's available if you were to use external DRAM. So in the middle here, we see a very popular choice, which is high bandwidth memory. It's a relatively new style of architecture that depends a lot on stacking. And what's interesting about it is it provides the highest bandwidth of any kind of external DRAM, and it's also got very good density. The challenge is it's more difficult to design for, and it has additional costs. And so it can be a great solution as long as you're willing to tolerate those costs and the additional design difficulty. And on the right is a GDDR memory, which has been in the industry for a couple of decades. It was originally developed for the graphics market, which needed very high bandwidth. But there are many AI applications that are using GDDR. It's got a great trade-off between performance and power efficiency and implementation complexity. And so there are many people who choose to adopt it because it's a better choice than for what their solutions would be able to use with HBM. The key here is that there's a lot of trade-offs to really think about. And as designers and chip architects think about what the most important metrics are for their chips, they choose one of these memories, typically, that's kind of the most appropriate for their application. The upshot is that the memory choice is really a key system architecture driver, and it really drives a lot of the other choices that you make in your design. So there's multiple options out there in the market, and they're really suited to different needs. And we see that this is going to continue into the future, and memory performance is going to keep being driven up, basically due to the needs of future AI applications. In this slide here, I'm showing some of the key trade-offs that can happen when you're building a memory system out of either GDDR6 memory or HBM2 memory. And what I'm showing is SoC implementations that would like to get 256 gigabytes a second of bandwidth. And on the left, what you see is how we would do this with a GDDR6 memory system. What I'm showing is 4 DRAMs. Each of them have a 32-bit data bus into the SoC. And these DRAMs themselves each can provide at 16 gigabit per second data rate, they can each provide 64 gigabytes a second of bandwidth. Since there's 4 of these devices, that's an aggregate total of 256 gigabytes a second. On the right, what you can see is an HBM2 implementation, where what we have with HBM2 is just a single DRAM device. And that single DRAM device is much wider in terms of its memory bus. It's 1,024 bits, and it runs at a lower data rate, 2 gigabits per second. But again, the aggregate bandwidth there is 256 gigabytes a second. The table below actually talks about what some of the trade-offs are in terms of using both of these technologies. One of the first ones that we see is that the per pin data rate is much different. GDDR6 is much higher than it is for HBM2. And also GDDR6, there are specific circuits called the PHY, which need to be on the SoC in order to talk to each of the DRAM technologies. In the case of GDDR6, we find that the aggregate PHY area is about 1.5 to 1 3/4 times the aggregate area for the PHY in HBM2. So it does cost you more real estate in the device. In terms of the PHY power is also higher. So it's somewhere between 3.5 and 4.5 times as much PHY power to implement GDDR6. And so there are definite area and power advantages for HBM2. But where GDDR6 has an advantage is that it's simpler to implement. So HBM2 requires an additional interposer to manage the fine grain and the fine pitch connections between the DRAM device and the SoC. And there is additional components that need to be stacked. And so that stacking adds complexity and cost. And so these two things, the additional interposer and substrate that go along with it, and the additional stacking that happens both in the memory devices themselves and of all the components that build up the system, they lead to complexity and cost advantages for GDDR6. And so these are some of the examples of the different design trade-offs that a chip architect and a system designer need to think about. And you can see how they can drive some of the various decisions that go into choosing what the right memory is for your system. One of the interesting things that's been going on is how AI training has been evolving in the data center. And one of those evolutionary steps has been the increase in the use of parallelism to train neural network models. So in earlier times, individual neural networks were trained on a single training engine. And what would happen is a very simple case, but what would happen is the model would be put onto a processor, and then the data set, the training set, would be streamed through that processor, and the model would be trained, and it would its ability to classify and perform would improve over time. One of the things that's interesting about this kind of an implementation is that the performance really depends on the speed of the compute engines and of the caches, and as well as the performance of the memory system in terms of being able to move that training set on and off the processing engine as quickly as possible. But as training sets have evolved in size and gotten much, much bigger, and as the models have become more complex, there's been a desire to use multiple engines to try and really train some of these models. And one of the methods that's in use today is data parallelism, where the model itself is replicated among the various compute engines. And what we do, instead of having the entire training set be on one processing engine, that data set's actually partitioned. And what happens is, in this particular example, 1/4 of the training set is given to each of 4 different processors. And they go through 2 phases. In the first phase, each processing engine will train its local copy of the neural network model with its fraction of the data set. And then what happens is each of the neural network engines will then communicate those changes to each of the other engines involved in the training. And so there's actually a phase that goes on where there's a large communication step, where each of the processing engines need to trade their updates so that they can get a faster global change to the model. What's required here that's very interesting is not only does memory bandwidth matter for the training step, but what we also see is that fast communication links are needed in order to do this exchange of information once each engine is done with its pass through the training set. And so not only are memory interconnects important, but also chip-to-chip interconnects are important as well. And those two trends are going to continue into the future, where more memory bandwidth is definitely going to be needed, and of course faster interconnects are going to be needed as well. Another really interesting challenge is that I mentioned before is just that the size of AI models and training sets are growing. There's an interesting quote that came from Intel when they spoke at their AI summit in 2019, and that was really the observation that the number of parameters in a neural network model was growing dramatically, on the order of 10x per year. And that's really faster than any other kind of technology curve. So memory capacity isn't growing at a rate of 10x per year, and neither is memory bandwidth. And so really the size of the models are really stressing the ability of memory systems to keep up. And there is this relentless demand for more memory bandwidth and capacity, not only for the size of the models, which I've shown here, but as those models grow in size, the training sets grow in size as well. And so being able to both accommodate the much larger capacity of the training sets, as well as to increase the bandwidth and to push those training sets faster into the compute engines is a key challenge for memory systems. Just by way of comparison, just a year ago, we were seeing that some of the largest models, OpenAI's GPT-3, was about 175 billion parameters, and we've already crossed the 1 trillion parameter size of some of these models in under a year. And so the number of parameters in these models continues to grow, and we're continuing on that 10x per year curve. And so again, going forward, capacity and bandwidth are going to continue to be really stressed in memory systems. The industry has, for a long time, been looking at other techniques, things like reduced precision, quantization, and sparsity. And those techniques are going to become even more important going forward as the models continue to grow in size, and it becomes harder for processors and memory systems to keep up with those capacity demands. Another key challenge here is really energy efficiency and data movement. And so this slide here is kind of a well-known slide that depicts some of the problems. And so what you can actually see here is this bar chart. It actually shows you the amount of energy required to add two numbers together in a 45 nanometer process. The red portion of that bar is the actual act of adding numbers together. And the blue part is everything else that's required to set up that add. And what we find is that it's an incredible amount of energy just to get to the point where we can add the numbers together. In fact, it's dominated by that. We can see there's a fair amount of energy required in the control, but there's a lot of energy required in terms of getting to the instruction itself and to get to the data that we need. In fact, in this particular example, the 6 picojoules, which is shown here, is if you're lucky enough to have those pieces of data be resident on chip in your register file. The challenge is if you have to go off chip to get the data. And you can see in the tables up here, the amount of energy that's required to go to external DRAM can be on the order of 3 orders of magnitude more energy. And so it gets to be really challenging if you have to move data around from off chip. And so what we see now is that this trend of where compute used to be the limiting step in terms of energy efficiency. It's now data movement, and this is really why we're seeing a resurgence in interest in new types of computer architectures. And these architectures are really designed to try and minimize that data movement and to really spend much of their effort and their energy on trying to compute as much as possible. So rethinking these architectures is going to continue as we go forward. And it's really going to be in part based on helping to minimize data movement and to use the memory capabilities as efficiently as possible. So one of the challenges that I mentioned is this data movement. And the question is, how can we make memory systems, and in particular DRAMs, much more power efficient? And so I mentioned there is this tremendous demand for more memory bandwidth. That's not going away. We're watching those standards evolve very rapidly from GDDR6 to GDDR6X and HBM2 to HBM2E and future standards. And this is happening at historically faster rates than we've seen in the past. The other interesting thing is that SoC power budgets, we're actually seeing that these PHYs that I mentioned before, if you look at the power budgets, some SoC designers are reserving 25 to 40% of their power budget just for the PHYs. And so clearly something needs to be done to try and address this challenge. HBM really is the most power efficient kind of external memory that provides a high level of bandwidth for AI. But still, really a large portion of the power that's used by HBM is spent moving data. And so this pie chart on the right here actually shows what that fraction is. And the pie chart is broken down to show how much energy is typically used just to access the bits in the DRAM core itself. And then in the blue portion of the pie shows how much of that energy is spent in the SoC PHY to move the data back and forth. And then in the lighter tan shade, there's an analogous kind of interface on the DRAM that helps move the data back and forth across the wires. The most important thing is we need to access the DRAM core. And the other portions of the pie chart are really the consequence of moving that data over some distance between the DRAM and the SoC. So what we see here is that really 2/3 of the power that's needed to access data is really just in the movement of the data itself. And so that's the largest part of the pie that we need to address. What the industry is looking at and what's a popular topic in research now is stacking, where we can really minimize the distance that the data is being moved. What stacking can do for you is it can provide more IOs because you get an area kind of interconnect if you were able to put the memory on top of the SoC. But it does introduce some new challenges, things like thermals and figuring out how to scale both capacity and bandwidth at the same time. And then, getting to really good power efficiency is a challenge as well. This is an open research topic, but the industry is looking very carefully at this because of the amount of energy that's spent moving data. And this slide here talks about some of the physical challenges that we see. And on the left here is just a partial list of some of the different kind of physical effects that really come into play as we go to faster speeds. And really, in order to ensure very good signal integrity, as we go faster in moving that data between memory and processors, there's more effects to take into account. And what that means is it's much more important now to have accurate modeling so that by the time you actually make your system, you can really get what you were expecting to get. And what you see in the middle here is the evaluation board that Rambus created for our GDDR6 PHY. And by modeling all of the various effects, accurately, we were able to achieve the kind of signal integrity and clean transmit eyes that we were hoping to see. And you can see an example of our transmit eye diagram at 18 gigabits per second here. There are a number of other interesting studies that have gone on, and really what it comes down to is in your modeling effort, you have to think about some new techniques to manage the signal integrity. And on the right here, and you can see some examples of some things that have been done. This is an example from a presentation by Micron, showing some of the really innovative things that have been done in order to help improve signal integrity. And there's a lot of great work going on in the industry right now, and it's really helping to lead the way for faster speeds to be achieved. All right, this brings me to the end of my talk. And just in summary, really there is this increasing connectivity that's driving growth in the amount of digital data in the world, and it is driving some change in the way that data is processed. We expect that those trends are going to continue going forward, and there's a lot of new, interesting architectural opportunities that we see, especially things like CXL. Things like memory systems, that are going to be in the near future and further out, where they're going to continue being bottlenecks in terms of performance and capacity for all kinds of applications that we see in the data center and also for AI. There are going to be these physical challenges in trying to improve memory and interconnect performance and power efficiency, especially to meet the needs of the highest demand applications like AI. But we're going to continue to be driven by a need for better performance and better power efficiency, and especially total cost of ownership and total cost of operation. They're going to continue to influence the way that these architectures evolve as well. It's a really exciting time to be in the industry. There's a lot of new interfaces coming to market, and system architectures continue to change in order to address these challenges. And memory systems are one of the most interesting, hottest areas right now to be working in. Thank you very much.